For the section 4, general second order system. Should be analyzed. Okay. For the second order system, we can define the transient response of the system. Okay. Using two coefficients, while first order obeys 1 tau. Okay, because in the first order system we have the one pole and one time constant, but in the second order system we have two time constant. Okay. For the first order system, Gs is equals to the B divided by S plus A. Okay, and so this yields, or the taking the Laplace transform, inverse Laplace transform, yield us this kind of response: B times E over AT. Okay, this is the GT, or B times E over minus T times 1 divided by tau, because 1 divided by tau is equal to the A. Okay, and so the two concepts should be given in here again, are natural frequency and damping ratio. Anyone knows that? Damping ratio? Just remember the system dynamic lesson. What's the meaning of the damping ratio? Or natural frequency? Doğal frekans? Okay. The natural frequency is that this is the frequency of the system. This is just kind of oscillation energy. Okay, but damping ratio is directly related to the what? The loss energy. This is called the zeta. Anyone remembers the zeta? Zeta is 1 is damped, 1.2 overdamped, 0.8 underdamped. This is the directly scaled condition for this case. Okay, and so this is defined with the what? Exponential decay frequency divided by natural frequency. Okay, in time we don't have any oscillation components if damping ratio is greater than 0, because it loses. Okay, the transient response goes to the what? Goes to the 0. We lose the energy. Okay, but the forced response every time happens in here. Okay. And so in order to understand these concepts, we need to revise our solution. Let's revise our system. just like this one. GS is equals to the B divided by S square plus AS plus B. Okay? These are the second order system. But if you don't have any damping, this looks like to what? B divided by S square plus B. Okay? Because in here S1 and S2, the roots imaginary, right? If we have the imaginary, always happens the oscillation, right?
So the B over S squared plus B, both roots are imaginary, so it's undamped, right?
Yes.
So it's gonna always oscillate.
Yes, always oscillate. But in this system, we have the zeta. Okay? And so, what's the root of these terms? The roots are equal to the S plus A divided by 2 plus square root of A square for B divided by 2 times S plus A divided by 2 minus A square minus 4B divided by 2. This is the extension or expansion form of the formula for the poles, okay? But in this case, we have S plus J square root B and S minus J square root of B, okay? This is undamped, but this is damped, right? Okay. And so, what about the zeta?
Zeta was related to the omega value, which is
Yes, it's related to omega, but it's different from it. Okay? It's derived from the.
derived from them.
Yes. Exponential decay. Frac divided by natural frac. And so it means that we have the sigma component at the real part on the S plane, and we call it the Wn for the natural frequency, and so A divided by 2 because it's the real root. Okay? The other one may be imaginary because we have the square root in here. Okay? And so Wn is given in here, and just see that in that case Wn is equals to this one, because this is the oscillation frequency for this pole, right? Because the oscillation happens coming from the what? The imaginary part. And so the root is J times square root of B, and so Wn must be equal to this one. Okay? This is the oscillation frequency.
The square root of B, this is going to be the peak of our cosine.
No. See that? For this case, this is just kind of sinus, right? And so maybe this is the A, and A times sinus 2, or I'm sorry, this is equals to the square root B T. This is the frequency. Okay? And so, if this is the case, and Wn square is equals to the B, right? This is the B. And if the Wn square B, and so we can derive to this one. A is equals to what? 2 times zeta Wn, right? Because the equation is coming from zeta A divided by 2 Wn, and so if you reorganize the equation, we will have it. Okay? And therefore, we have the A, we have the B in here, and so this GS can be rewritten with the what? Wn and zeta. And so what's the values of the B in here? Wn square, right? Wn square. And so we have also S square plus and plus Wn square, because we have the 1B in here. But what about the A? See, This is the A. And so Q, zeta, Wn, S can be given in here. Guys, this is the general form of the second order system in terms of the what? The Wn and the zeta. Okay? And so the root of these terms S1 and 2 is equals to what? Minus zeta Wn plus minus Wn zeta square 1. If you apply the second order root rules in here, you will get it. The root of these terms is equal to what? To this one. Okay? Yes, natural frequency for your system. And so we can show these terms in here, just like this one. This is the graphical representation of it. See, zeta and pulse and step response. And so, what about the zeta 0? If the zeta 0, see, from the previous slides, we can write the roots in here just like this one. S1 and 2 is equals to the minus zeta Wn plus minus Wn square root of zeta square minus 1. Okay? And so, what happens if I choose the zeta 0? This going to the what? 0. This going to the 0 and plus minus Wn square root minus 1 or J, right? And so we have two roots in here, just like this one, minus JWN, JWN, okay? And so what's the response of this system? Undamped, which means that we have this kind of oscillation, right? Yes, sinus Wn times T. Okay? And so, what about this one? If the zeta is between 0 and 1 in here, and so we have another pulse in here. This is the real, this is the imaginary. Okay? From this formula, we have two poles in here. And so, what's the values of this one? The real part is this one, minus zeta Wn. And so, what's the values of this term? At the imaginary part, Baran? And so, Jwn times square root 1 minus zeta square. This is different. But why? Because we have the zeta in here 0 and 1 and it's always negative in here, and so J times this one yields this one. Okay? Minus J Wn 1 minus zeta square. And so what about the response of these terms? Yes. If we have the last final positions, and so we have this kind of response, right? We have some oscillation, but it diminished. We lose the energy because the zeta is greater than 0. See? Yes. Yes, this is the overshoot. Okay, and so we will formalize it. Okay. And so, what about this one? Zeta is equal 1. And so, where is the poles right now? If zeta is equal to the 1, this yields us to the what? If zeta 1, 0. And so we don't have any imaginary part, right? And so we have two roots at minus zeta wn, right? And so what about this? This is looks like to the what? T, ct, right? And so this generates to this one. We don't have any oscillation in here. And so we will call it critically damped, right? This one, underdamped. This one, undamped. Yes. What about this one? Zeta is greater than 1. This, yes, overdamped. This creates the what? Right now, the real part, not the imaginary one. Okay? And so, if we redraw these terms, imaginary one, and this is equals to the what? This one and this one, because the one of them plus, one of them minus, and so this one is equals to the zeta omega n minus wn zeta square minus 1. This one minus zeta omega n plus wn zeta square minus 1. Okay? And so what's look like in here? T and ct. This is overdamped. Like this one. Maybe this one. Okay? But this is overdamped. So, if the specification of the system are provided, we can condition the R system in terms of the what? The zeta and wn. And so, we can design the overshoot, settling time, and the other parameters based on this one. Okay? Because we know this shape. If we can use this one, and so we can drive everything based on these notions. Okay? And so, what about this? In the section 5, we should talk about underdamped second order system. For underdamped response, the unit step is Cs is overs to the what? 1 divided by S times, in here, if we have the second order system, we can generalize it, Wn square and S square to zeta Ws and Wn square, right? Because this is the general form. Okay? Maybe zeta is 0.1 or Wn is 1. Maybe zeta q or Wn 0.2. But this is the general form. Okay? We can write it. If we apply the unit step response, and so we will get it in general form. Any type of the second order system is equal to this one. Okay? So, what about this? K1s plus K2s plus K3 divided by S square to zeta Ws plus Wn square. What is it? It's splitting into two parts because we can do this, right? We can generate the more response based on these terms. These two identical, but we don't know right now the K1, K2, and K3. we should solve it, right? But we can write this one. But why? Just see that this is the forced response, right? This remains always constant in this system because the unit step response. This one is temporary, which means that natural, but natural means the transient response. In Turkish geçici, diğeri kalıcı. Steady state kalıcı, transient geçici. So this is transient. Okay? And so how can we analyze this system right now? CT, and we can draw these terms in here just like this one, and so we have maybe the CF, final C value. If we are going to do what some steady state points, and so this is called CF, but we don't know the values. This is the generalized parameters, maybe 5, maybe 10, but it's not important. Okay, it's a variable, constant variable. Okay, and so this one is that, and also if this is the underdamped, which means that if this is the underdamped, and so this looks like this one, right? Because we know it. If this is the underdamped, this looks like this one, right? Always happens this kind of generalization, okay? And so what about this? This is the what? Peak time, right? And so if we draw it, this is the T peak because it's a peak, okay? And so just remember the first order response. We say that 0.2% of the final initial values or the final values is equals to a settling time, right? And so we need to draw also these things in here just like this one. See this point, and so this is the settling time. And so what's the values of this term? 1.02 CF, and this one is equals to what? 0.8098 CF, right? These are rule, okay? And so what about the rise time? Rise time is an important parameter, and it's defined with the what? With this one. 0.9 CF is equals to the what? This one. And so also we can define 0.1 CF, this one, and so the rise time is defined this one, okay? This is the general assumption for the R underdamped second order system, guys, okay? I cannot define this one. This is the literature definition, and we should use it, okay? In Turkish, bunları ben tanımlamıyorum arkadaşlar. Bunlar var ve sabit bunlar. These parameters are always constant and happens at every underdamped second order system, guys, okay? So, but if we have this kind of information, and so we should define another parameters in here. For example, this is the what, this is the steady state values in here, and so this one is defined the overshoot, okay? This is settling time, and so therefore we need to or if we write this one, and so we can give this one. Therefore we need to find T peak, overshoot, TR and TS, right? This overshoot in the percentage format. Okay, so first of all we need to evaluate overshoot. Okay, overshoot is given by, how can I define the overshoot in here? This is the C max point, and so how can I find or define the overshoot in this system? This point is C max, this point is CF, and so help me to write the formula. The percentage overshoot is equals to what? Yes, C max minus CF divided by CF times 100, right? This is the overshoot. Okay? And so if we apply the unit step in this signal, we can derive it using CT. If you are taking the Laplace transform, inverse Laplace transform, this equation looks like this one. 1 minus 1 divided by square root 1 minus zeta square times E over minus zeta Wn t times cosinus Wn 1 minus zeta square t minus phi. This is the fuzz, okay? Fuzz degree. But if you taking the inverse Laplace transform, this equation yields us, okay? Do you get it? You don't need to solve this equation right now, but you just know that the CT solution is that, okay? And so what about this one? At TP, peak time is the C max, right? We know it. And so CTP is equals to the what? 1 plus E over minus zeta W square root minus zeta square. Okay? We know it. Because if we put TP as T, and so this is the TP, this is the TP, and so this equation gives us this formulation right now, okay? And so we always know that the CF is equals 1 in here because we have the 1, right? So, and this equation returns to the what? This one. The percentage of os is equals to the what? I'm sorry, it's too complicated, complex formula. Os percentage is equals to the what? 1 plus exponential term minus zeta pi divided by 1 zeta square minus CF divided by CF. What is the values of the CF? 1. And so this one and this is 1. And so it yields us to the what? E minus zeta pi divided by 1 zeta square times 100. Right? This is simple. Okay. And so the percentage of the os overshoot can be calculated with the what? With this formula. E minus zeta pi divided by 1 zeta square times 100. This is our general formula for the what? Underdamped second order system. What about the zeta? If you solve the zeta from this notion, and so zeta is equals to the what? Minus ln percentage os values divided by 100, okay, and square root of pi square plus ln square os divided by 100, okay. This is the solution of the what? The zeta in terms of the os overshoot, okay. You don't need to drive this equation, but you should know it because it's too important. If we have any time response, and so if we can measure the overshoot, just see that if we can measure the overshoot, and so we can calculate the zeta. This is important, and so we can drive our general second order response for a given any data set, time response, right? Any question? No. I will give that formulas.
So, if you have the overshoot, you can calculate zeta, and you can find the critical response, right?
Yes, but this is the underdamped solution. If you have the critical damped system, and so you don't have any overshoot, which means that zeta 0. You should know it. You already know it. But if you have the underdamped system, you must use it. Okay? So, what about this one? Evaluation of TS or settling time, right? And so for CT, we can write this one. CT is equals to the what? 1 minus 1 minus zeta square times E minus zeta WNT times cosinus WN 1 minus zeta square T minus phi. Okay? This is our general solution for the CT. But we know it from the diagram. Just remember that. We have this response, and so what is the settling time? Settling time means that we have the steady state values in here, but the steady state value CF between 0.98 CF and 1 divided by 1.02 CF values, okay? If we are going to infinity values, and so the R signals in here, and 2% error between the what? The steady state value is our settling time. Do you get it? Just see that. See? For example, we have the 1 in here, and this is the 102, and this is the 98. And we drove this signal in here, just like this one, and this point is the what? TS, right? Right? Settling time is equalized to this one. And so, which means that this is the what? The final value. And so, what is this? Or what's the values of this term? This is the amplitude of the cosinus, right? And so, in order to find out what is the settling time, this should be equals or smaller of the what? 0.02. Right? Because this is the final value, but we know it if we have the 0.98 or 1.02 in here, and so this amplitude should be or equals to smaller than the 0.02. Just see that this is 1, for example, if we minus 1 minus 0.02, which is equals to the what? Yes, if this is the minus, and so 1 minus 0.02, which is equals to what? 1.02, right? And so we should solve it. So if this is the case, and so we can write this one. This must be equals to the E over zeta wn t 1 divided 1 minus zeta square, which is equal to 0.02. Okay? And so if you solve this equation in here, this t is right now ts, right? Right? Because the t must be assigned to ts, and so this term is equal to what? 0.02. And so solution of this term ts is equal to minus ln 0.02, I'm sorry, 0.02 1 minus zeta square divided by with the what? Zeta w. Okay? But this is too complex because we have the 0.02 term in here. This is too small. Generally, in literature, in the control literature, we can make the some assumptions, and ts is finalized assigned to the what? For zeta wn.
TS means when the system approaches steady state.
Yes, but with the error rate of the what? The 0.02.
The error 0.02, this is for all underdamped.
Yes.
Second.
Yes. Yes. For every underdamped second order system, this must be current.
In the first order system, it was also.
You don't have the any setting time in here because you know it to the what? Time constant. If you have time constant, multiply for the 4, you get it. Because we know it in the first time constant system. See that? We know it 1 divided by a, or tau is equals to what? 0.63. You don't need to compute anything in here because in the first order system we know it. But in the second order system you need to know it. Okay? In some assumption, these terms is equalized to the what? To this one. This is the basic assumption. Okay, guys? Okay. The evaluation of TR is equals to the what? In the, we should know that we cannot directly obtain this value. But TR, it's calculated from the graph. It's equalized to the what? 1.8 divided by Wn. This is also another assumption for the underdamped second order system, guys. This can be proved, but it's too long. Rise time. Rise time, see. This is the CT, for example. This is the 1. Okay? And so we have this kind of response in here. That's like this one. And so we have the 0.1 and 0.9. Okay? Because 1 is the CF, the final CF. And so we have one T1. We have one T2. Rise time is equals to the what? T2 minus T1. This is also another important parameters to drive your system. Okay? Yes, the rise time means that the time or the duration of the what the final response is equalized to the what the 90% from the 10%. Hayır. Hiç öyle düşünmeyin. Bakın. Yükselme zamanı ne biliyor musunuz? Burası 1 ya. %10'dan %90'a kaç saniyede yükseliyor? Rise time bu. The rise time is that the duration between the 90% or 10% to 90% duration for your sequence. See, T1, T2, rise time, T2 minus T1 in here. And so you can drive. But you can assert or calculate based on this formulation. This is the current approximation method yields us this formula.
This is always between 0.1 and 0.2.
Yes.
From 10% to 90%, the rise time can be 1.8 over W.
Yes. You can assert, but this is not be true, but it's close. Okay? These are the assumption, approximation.
Is there certain scenarios where this approximation is more accurate?
Yes, but in the project you will calculate this already. Okay. And so in your project you will notice that this formula is not true. But in your time response also is not true. You need to approximate the some basic conditions. You need to design, you need to optimize your second order system based on this one. Because we don't have the exact model, correct model. But also everything is an approximation in this case. Okay? Because we don't have the perfect solution. But we may close it. Okay? Any question? Please, in your book, required reading is done with the what 4.10 and 4.11 section. Okay? You need to read the NISA book for these sections. This is the complementary section about the R time response characteristics. Okay?
Does it also contain the proof for 1.8 over W?
Yes, we have a proof at this moment, but in the book. But we don't have the exact proof. It's also approximation, not the exact one, analytic one. Okay? Any question? Hayır. Hiç.